So welcome back. Up to this point, we've done 4 days on the R basics section of the course, and we've talked about R's basic data types, including numeric, so that's just basic numbers, character strings or characters. Those are things that are enclosed in quotes and represent textual data. So we've talked about vectors, which are created using the lowercase c function, and those are really the core data type in R. So things are vectors unless there's something else, is kind of the way you should think about it. List types, which are designed to be more flexible than vectors in that they can combine data of different types, and data frames, which are a special example of lists where each value is a vector, and the vectors are going to have the same length, and these are intended to represent tabular data, where the vectors stored under each name are the columns of the table. So today we'll talk about one more R topic, which is programming in R, and then we'll begin our discussion of some data science specific packages that we'll use called the tidyverse. So I might go a little bit quickly through the programming stuff because, as we're going to see, we'll mostly figure out ways to avoid having to use these features. It's usually going to be cleaner and more efficient to do that. However, sometimes you will need these skills, so we're going to go ahead and make sure that they're included here so that you have some reference for that. So R is first and foremost a data analysis environment, but it is also a programming language. So that means it's got all of the features that you need to implement, in principle, whatever you want, whatever computer program you want. And these core elements, at least as they're represented in many programming languages, to achieve the ability to perform tasks repeatedly and dictate control flow, in other words, determine which blocks of code execute under which conditions, we're going to need loops. In particular, we'll talk about for loops and conditional expressions, so if statements, as well as functions as a really important code organization tool. So these are key building blocks for doing advanced programming, but sometimes, as I said, you will need them during data analysis. So it's important to know that you have those available if you want them. So we'll start talking about conditional expressions, or in other words, if statements. So these are one of the basic features of programming, and you've seen them before if you've done any programming before. They're used for what's called flow control. So this is determining how the program executes based on values that are accessible within the program. So the most common one, as we said, is the if-else statement. So in R, we can do a lot of stuff without conditionals, but they do come up sometimes, and it's important to be able to use them when you need to. So here's what an if-else statement looks like, a basic if-else statement in R. So this might look similar to what you've seen in other languages, maybe a few differences. Let's go ahead and run that. Yeah, so this might be similar to what you've seen with a few differences. So we have these curly braces enclosing the various parts of the if statement. So we have if, and then in parentheses, we have some condition. The parentheses are important here. And then we have some block of code that we want to execute if the condition holds. So if A is non-zero, we'd like to print the value of 1 over A. Otherwise, we want to say there is no reciprocal for the value that we put in. And we know if we're in this block that the value must be 0, because if it were non-zero, only this part would have executed. And so we see that's exactly what happens when we run this code. And if we try assigning a different value, then exactly as expected, we'll get the value of 1 over A printed here. All right, let's look at an example with our DS Labs murders data frame. So we'll store the murder rate we'll divide the total by the population, multiply by 100,000. We'll store that as murder rate. So we've done that before. And we'll do a conditional statement here so you can see what this looks like. So let's say that we're trying to figure out whether there's a state with a murder rate less than 0.5. So we'll determine which state has the minimum murder rate by finding the index of the row with the minimum murder rate value, store that as IND, and then check if it's less than 0.5. And if so, then we'll just print the state name. So we'll grab from the murders state vector the corresponding entry and print that. Or if there's no state with a murder rate below 0.5, we'll print that out here. So that's just a simple if-else statement. And we find that indeed Vermont has a murder rate less than 0.5. It's got the lowest one. And so we go into this first branch and get the value of the state printed. However, if we did it again with a rate of 0.25, that is actually lower than Vermont's rate. So if we run this code, it's going to say no state has a murder rate that low. So this branch of the if-else statement is the one that executed. Now, one problem with doing all of your if-else work with this block structure, so the if statement and the condition in the parentheses, and then you've got these two sets of curly braces with the else between. So the problem with using this as your main or exclusive if-else construct is that it doesn't work on vectors. Notice that we needed to be looking at a specific true or false value here, one single true or false value in these parentheses for it to work. In these parentheses for it to work. If we want to do it entry by entry for a whole vector, then we need another construct, and that construct is the if-else function. So it's a similar idea. It takes a condition as well as a value to take on if the condition is true, as well as a value to take on if the condition is false. So we can see that it works just like the block construct here above if we use it for a single value. So A here is 0, and if we're checking is A greater than 0, it's not. And so this value in this expression here is what gets returned. So we get an NA back. If we change this value, then we would get 1. Now, the advantage of this particular version of the if-else functionality of R is that it does work entry by entry. So we can apply this if-else function to an entire vector, and it works just fine. So if we define this vector that has 5 entries here and check if greater than 0, reciprocate, otherwise return an NA, then we get an NA in exactly the positions in the vector where the value was not positive. So there's 0 here and this -4 here. So that all makes sense. You could not do this, at least not without more pomp and ceremony, using an if-else statement. You need this vectorized single function if-else to do this. And since, as we've learned, vectorization is very important in R, you will most often be using if-else rather than the full control flow construct. So here's an example to show how you might use the if-else statement to replace NA values. So in our NA example, if you recall, there are lots of NAs in this vector. So if I pull up my cell here and we'll just remind ourselves what this vector looks like. So there are lots of like 1s, 2s, 3s, and 4s, and then a bunch of NAs. And let's say we want to replace all of the NAs with 0. So what we can do is we can run if else and then check. So we'll return a logical vector containing containing truths exactly where there are NAs. And then we'll choose the 0 value if this condition holds, if it is an NA, and otherwise we choose the corresponding entry from the NA example vector. So this is a simple way to replace all the NAs with 0s, and you can see that's what's happened here. Everywhere there was an NA, there's now a 0. So one thing that might be a little confusing here is that this 0 value is just a single number, and this is a vector. So something a little fishy is going on here. This is not, it's not as straightforward as it seems. So I want you to think about it because we have talked about exactly what's going on here. So here's the basic form of if else. You run it on a whole vector, and then wherever there are truths, it selects corresponding entries from the first vector, and whenever there are falses, it selects corresponding entries from the second vector. So here we have 1, 5, 3. What feature of R enables us to replace a whole vector here with a single number? So we have actually talked about this in a different context. Let's see if you can put it together. Okay, so I'll start sharing some of the answers. Several people had great answers here. All right, cool. So the term for this is recycling, and some people use the term, other people described how it works, but yes, this is exactly what's happening. Whenever you have one vector shorter than another for a vectorized operation in R, what R will do is go back to the first entry. Once it goes off the end of the shorter vector, it will go back to the first entry of that vector and go through it again. So for example, to make it really clear, this is exactly what's going on. Let's say instead of a single value here, we put in two values, 0 and 100. So if we do that, if it's in an odd index position, it gets replaced by 0. If it's in an even index position, it gets replaced by 100. So here, there's a 2 being compared to, a 0 and a 2 vying for this position, and a 100 and a 1 vying for this position. And whenever this one is a number, it works out. But here, there's a 100 and an NA vying for this position. And since the NA value puts a true in the corresponding position here, the 100 gets selected, and so on. Okay, two other useful functions in the context of logical arrays. So two other useful functions we have when dealing with logical arrays are the any and all functions. So we often want to check, is there any true value here, or are all of these values true? You can do that with the any and all functions. So for example, if we look at the vector true, true, false, and we ask any of z, are there any trues in there? There are two in fact, but there's at least one, so we get a true, and all of z returns false, because it's not true that all of the values are trues. Okay, so let's talk about defining functions. So you might, as you build more advanced code, you'll often find yourself performing the same task repeatedly. And the easiest way to deal with this is to just copy paste code over and over. And you probably have done that early on in your programming experience, if you have some programming experience. And this is not considered good style, because if you need to make a change, you now have many places where you've copy pasted the same code where you need to make that change, and it gets very cumbersome. So your code will compose better, and you'll be able to build more elegant and maintainable programs if you package these reusable components in a manner that allows you to define them once and then use them wherever you need them. So the programming idea for that is called a function, and we'll see how to define them here. So we've used many functions from R, but we haven't defined one yet. So let's do a simple example that we already have built into the language, but we'll repeat it. So consider the averaging function, which takes the sum of a vector as well as the length of a vector and divides the two results. So this is a simple function. It's so simple that it's built into the language and we don't need to define a function for it. But for the sake of checking that it does the right thing, we will use this one. So here's the syntax in R for defining a function. So we use the function keyword, and then in parentheses, we list any arguments that we want this function to have. And then in curly braces, we write the body of the function. So this is the code that should execute whenever the function is called. And we can refer to the arguments in the parentheses anywhere in this function body. So what we're going to do for this particular function is sum the input vector, assign that to the variable s, find the length of the input vector, assign that to the variable n, and then return the quotient s over n. So we can put several lines in the function body here, and they'll just execute one after another. Now, all that being done, so all of this portion of the code is creating the function. But of course, we want a name associated with the function so that we can actually use it later. So then we assign that function to the name AVG here. So we choose that name because mean is already taken, and we'll be able to compare the two. So we've defined this function now, and we can check that it works. So let's consider the vector of values from 1 to 100, and we'll check, is it true that mean of x, which is the built-in R function, is equal to average of x? And we'll check that using the identical function. The identical function is a way of checking whether two objects in R are exactly equal to one another. And that's a new thing. We didn't do equals equals. What's the problem with doing the equals equals here to just check whether these two objects are equal to one another? Yeah, so the correct answer is that the double equals is a component-wise operation. So this is a point about vectorization being really central to R. Most operations are vectorized, including the equals equals operation that checks equality. And that means that if you're going to use it for mean and average, so I'll show you exactly what that looks like. So if we do mean of X and average of X, oh, sorry, I actually messed this one up. So this is this is wrong. This actually works totally fine for this example. So this was a bad example to illustrate my point. However, the point does hold, because if you want, for example, to check whether 1, 2, 3 equals 1, 2, 3, of course it does, but you get true, true, true here instead of just a single true to say that these two vectors are equal. So in general, your concern about using double equals would be that it is a vectorized operation. You can't distinguish wanting to check whether two vectors are equal from wanting to check whether each entry is equal. So you can achieve a similar effect as the identical function using all. So if you do all with the double equals, that's going to give you the same result. But in any case, the identical function is kind of nice because it is the canonical R way of checking whether two objects are the same as each other. So you can use them regardless of what the objects are, and you don't have to think about things like vectorization. Okay, so sorry for making that mistake. I just wasn't thinking here when I inserted this question. Of course, these are actual numbers, so double equals works totally fine. So yeah, exactly. The all function together with double equals would, in the case of a vector, would work the same. Identical is kind of nice because you don't have to sort of change how you're doing the comparison based on what type of object it is. Okay, so an important point about functions is that the variable assignments don't the variable assignments inside the function body don't interfere with variable assignments outside the function. So for example, if we assign 3 to the value s and then call this average function, it works completely fine regardless of the fact that we're using the same variable name outside as inside. So the average of 1 to 10 is 5.5. That's fine. S is still 3. So it didn't overwrite this variable, or and this variable didn't mess up what happened inside the function. That's really important because you want to be able to use functions without knowing how they're implemented. You pull a function in from a library, you don't want to have to read all the code. That would be extremely cumbersome. Yet, if the variables defined inside that function body interfered with your workspace, then you would need to read the code to make sure that you're not using the same variable names. This is a really important thing for a programming language to have. And the language here is scope. So I've mentioned this word a few times, but what we say is that a function body introduces its own variable scope. In other words, variable assignments in the body only take effect within the function's body. So this is a difference between R and some other languages, and we've mentioned this a bit already. Functions are objects. So when we use the function keyword together with the parentheses and the curly braces, and we define a function, we then assign that to a variable name. That's just like the assignment of any other object to that variable name. So functions are not special in the language with respect to how they work for variable assignment. The functions you define in R can have multiple arguments, of course. So you would just separate those with commas, just like you would when you call the function. And you can also supply default values. And again, you do that using the same syntax you use when you define, when you call the function. So if we want to have an optional argument here called arithmetic, or an argument with default value, we can supply that default value here. So this is now a different function than the one in base R. It takes a vector X that you want to take the average of, but then it lets you say whether you want the arithmetic mean, in other words, the sum divided by the length, or whether you want the geometric mean. So the idea is arithmetic equals false corresponds to geometric. And that's going to be the product, the nth root of the product of the entries. So it doesn't really matter exactly what geometric mean means. You can just take this for granted. But the point is that we're going to, in this case, let's use the if-else function. We'll check whether the argument supplied here was true or false. If it's true, then we grab the ordinary arithmetic mean. And if it's false, then we get the geometric mean and we return that value. So let's check that this works. So if we do average of 1 to 10, that's taking the default value of the arithmetic argument, and that returns 5.5, which is the arithmetic mean. And then the geometric mean is somewhat less than that. So that if you multiply the numbers 1 to 10 and then take the 10th root of that, you get 528, this number. So one thing that's going on here that might be a little bit different than what you're used to is that we can put the value that we want to return on the last line with no return keyword. So in other languages, you'll have a return keyword that may be required. In R, you don't. So for example, here, we have this if-else statement. So sort of two things are happening. So the if-else function here returns the value, whichever of these two values, in this position or in this position. It returns that value, and so this whole last line returns some value, one of these numbers or the other. And the function is going to return whatever value is output on the last line automatically. So we don't need to say return. However, it does happen sometimes that you want to interrupt the execution of the function to return some specific value. And you can do that with the return function. So it's not a keyword like in other languages. You need the parentheses here. So I think most other languages return as a keyword. Here, it's not. It's a function. So in any case, if you call, so we're going to create here a function which takes an input and checks is it bigger than 100. If so, it returns this character string, which tells us that our input is too large, whatever that means. And if not, then it returns the function that the value that we put in. So if we put in 101, we get returned this value. So this is sort of prematurely interrupting the execution to return some specific value. And if we put in a smaller value, then it gets all the way to the last line in the body and returns that value instead. And we're doing something a little bit cute here to illustrate the point of how functions are just objects in R that can be handled as any other object. So we can put this function in parentheses here and then immediately call it. So we're defining it and calling it in one fell swoop without actually assigning it to a name. So you wouldn't use that design pattern all that often, but it's just illustrating again that in R, you define functions with the function keyword and then do whatever it is that you want to do with it. Either assign it to a variable name, or you can call it immediately, or perhaps, as we'll see pretty soon, supply it directly to some other function that performs some task. And it's sort of nice that you don't have to use a name if you don't want to. So we will learn about creating functions more through experience as we encounter more complex tasks. Okay, so the next topic we want to talk about here is namespaces. So as you use R more and more, you're going to load more packages into your session to perform various kinds of analysis. And what can happen when you do this is that two packages will sometimes use the same name for two different functions. And often they'll do different things. So for example, we're going to learn about a package called dplyr, which is one of the most popular packages to use in R. And it has some functions that have the same names as some base R functions. So for example, there's a filter function available in R with no packages, just ordinary basic R. But then dplyr also has its own filter function. And the design decision was made, instead of coming up with some different name other than filter, to just mask the filter function from the base package, so that when you use filter, you are using the dplyr version, not the stats version. And when you load dplyr, so let's do that here. So if we do library dplyr and run that, it's going to say, watch out, the following objects are masked. And you can see there are several of them here. where a name has been chosen that sort of overwrites, or well, I should use the term mask because it doesn't overwrite, as we'll see in a minute. But it means that you can't just write filter to access the basic version. All right, so as we said, when we type filter, we get the dplyr version. That's what masked means. However, we might want to use the stats version, and you don't want to be completely stuck with the new version. You might have some specific use case where you need the old one. And what's happening here is that R follows a particular order looking up these names. So it's going to look through namespaces in a particular order. So the first one is the global environment where the objects that you define live. So if you define something, it's going to overwrite, or sorry, again, I shouldn't use that term because they are available. It's going to take precedence over any names in other namespaces, which are the same as that one. So it first checks the global environment where you've defined stuff. And then the order here is that it's going to check the dplyr package. That's because that's the last one we loaded. Before that, we loaded the DS Labs package. And then there are a bunch of packages which are loaded either because we're operating in a Jupyter environment here, or these are all basic ones that are loaded in R no matter what, just in any R environment. But in any case, R is going to go through these one at a time and ask, hey, do you have a name like this? And if it does, then it's going to use that one. So for example, filter, we haven't defined, so it's not going to be here, but it is defined in the dplyr package. So it's going to pick that one up. So if we type filter, I'll just show you, if we type filter here, it's going to get, well, you can't really tell where it's coming from, but this is the dplyr version. Fortunately, there is a way to escape this and specify which namespace we want our function to come from, and that is to use double colons. So this again is a little bit different than what you might see in other languages. But if we do stats double colon filter instead of just plain filter, then that's going to give us the built-in stats version. And again, you can't really tell here where they come from, but I can assure you this is the one that comes from the stats package, not the dplyr one. You can see here at least that they're different if you run it without the double colon. And if for some reason you wanted to be extra sure that you were getting the dplyr one, you could use dplyr double colon filter, and that's going to be the same as just filter by itself. One thing that is I think kind of cool about R that is not true again in other languages is that you can do this without ever loading the package. So if you want to use dplyr double colon filter, as long as you have that library installed, you don't have to have it loaded into your current session in order to use that. So if you want to use a single function just in one spot from a package somewhere, you do not have to load that package. You can just call this function straight away with the double colon syntax. Okay, so that is kind of the end of the functions and variables discussion. So I just want to ask quickly if you have any questions about any of the topics that we've discussed here. So there's a question from Marie, which says, you would need to install that package at some point, right? And that is correct. So it will not use the double colon syntax to go search for that package and try to pull it in for you. You will need to do install.packages. This is a good question. What's the difference between load and install? Yeah, so that's a question with a clear and important answer. It's helpful to make this delineation. So installing a package means putting the files that contain that package's functionality on your machine. So actually downloading the files from the internet or wherever they're coming from and putting them in a place where R can find them. So, and then once that's done, then loading the package means bringing it into your R session. So you can have it on your machine somewhere where R can find it if it wants it, but it's not loaded into your session. So for example, names that are defined in that library are not immediately available, at least not without the double colon syntax. And so the double colon allows you to essentially avoid having to explicitly load the package. So for example, there's a package we'll learn about called ggplot2 that has, well, let's see if I might have already loaded this. So yeah, that's, yeah, there we go. So ggplot2 has a function called qplot, and I just ran qplot here, and R is like, I don't know what you're talking about. This is not something that's available to me. But if we do the double colon syntax, then it will find that function. Or if we go ahead and load the package, then we can access that function without, we can go ahead and access that function without the double colon syntax. Yeah, so that's the distinction there. There's a question about, is there a way to change the order of the namespaces? And the short answer to that question is, I don't know. But R is the sort of flexible language that I would be surprised if there isn't a way to do this, even if it's some kind of ugly thing like assigning to whatever variable stores those. So just reordering them and then assigning back to that variable. I'm guessing there's probably some way to do that. If someone knows, let me know. I think in general, though, it is a bit dangerous to rely on that kind of functionality. I think that you want to, you use functionality that is sort of mainstream and very well supported. So use the double colons if there's any ambiguity. If you load a library and it masks something from the base language, it's totally fine to use that without the double colons, because it's going to consistently, of course, pull in the new library that you loaded over the base language versions of the functions. But if you start loading several packages that have the same name repeatedly and you're counting on the order being correct, to me, that feels a little sketchy, especially if you start messing around with the order. So I would tend to use double colons. Because what can happen is someone else can have your code and they can reorder things because they're playing around with the libraries for some reason, and then functionality starts changing. Okay, so next we're going to talk about for loops. This is our last piece of programming syntax that we're going to learn today. So earlier we talked about the idea of just adding up the numbers from 1 to n, and there's a typo here. Sorry about that. This formula is repeated twice. You just focus on this first one. So it's n times n plus 1 over 2. So like 1 plus 2 plus 3 plus 4 plus 5 is the same as 5 times 6 over 2. It works out, both of them work out to 15. So this formula is valid. But let's say we want to check it. We lack some confidence and we want to see that it works for a bunch of values of n. So one way to go about doing this is we can define a function, we'll call it compute sn, that just defines a vector of the first n integers and then sums them and returns that, because it's the value on the last line. So this is a perfectly fine way to do this for a particular value of n. So now if we do compute sn of some particular value, let's say 10, then we'll get 55, and that is what you get when you sum 1 to 10. So all that's good. But let's say instead of just picking some random numbers here, we wanted to do it for a bunch of numbers. Let's say all the numbers from 1 to 25. So we could do this by doing compute sn of 1, compute sn of 2, compute sn of 3, and so on up to 25. That's going to be very tedious. We would need to use some, search and replace functionality to change something if we wanted to, say, change the name of this function. And it's going to, especially as the complexity of our program scales, this approach is going to yield total uselessness. We're going to quickly reach a sort of, it's called spaghetti code, a state where we can't meaningfully make changes and reason about what's happening. So the way to clean all this up is to write what's called a for loop. So it's going to use a similar syntax as some of the other constructs we've seen, where we have parentheses followed by curly braces. So we have, in this case, the keyword is for, and then in parentheses, we have a statement that will produce an iteration. So we'll talk about this in a second. And then we have curly braces where we have the for loops body. So what's going to happen is this body is going to run repeatedly once for every value in this iteratable, which in this case is a vector. So I is going to be 1 first, and then this body is going to run. And then I is going to be 2 because that's the next number in this vector. And then this body is going to run, and so on. So unsurprisingly, when we loop through 1 to 5 and just print each value that we see, then we see printed 1, 2, 3, 4, 5. So nothing too surprising there. Let's look at an example with a little more complexity, namely this SN example that we've been talking about. So this is a new function that we haven't seen before, mainly because you kind of only would want it in the context of a for loop. And what it does is it creates an empty vector. So if we call vector length equals whatever, then we get a vector of that length that we can start assigning values to individual components of. So let's say we're going to look at 25 of these values. We're going to store that in the variable m. And then we're going to say, okay, we're going to give ourselves storage for m values so we can see all m of them. And we'll call this vector SN. So starting out, it's just got a bunch of zeros in it, specifically 25 zeros. And then as n goes from 1 to m, what we're going to do is compute SN using the function that we define. So like when n is 10, this will return 55, and we'll assign that value 55 to the nth entry of the vector S sub n. So when we do brackets in here, this pulls out the nth entry, but then if we assign to that, it will store something in the nth entry. And then we can see what the resulting value is. So if you sum the first one number, you get 1. The first two numbers, you get 1 plus 2, which is 3. 1 plus 2 plus 3 is 6. And then plus 4 is 10, plus 5 is 15, plus 6 is 21, and so on. So this seems to be working just fine. And we can decide whether this is equal to, whether these values are in fact equal to the n times n plus 1 over 2 formula that we've already looked at. Yeah, so again, what's happening here is that for each value of n from 1 to 25, we're just computing SN and then storing that to the nth entry of our vector, which starts out empty, and then we fill it up. Now, we could look at this in a more tangible way by plotting it. So let's do that. And what we see here is that we have this upward curve, this nice smooth upwards curve. And so this looks like a parabola, if you remember from whenever you learned about parabolas. And that makes sense with respect to this formula because n times n plus 1 over 2 is indeed quadratic. So that checks out. And you can also just check n times n plus 1 over 2 and see if it's equal to this vector. So we actually just defined n to be this vector from 1 to 25. So we can do n times n plus 1. That's all vectorized. And then divide that by 2. Again, these are vectorized operations. And we can see that this is the same as the values that we just computed. So these two are the same. And if you're not content just looking at them, as we saw, we can use the identical function. And here it actually is necessary because if you use double equals, it will be entry-wise. Uh-oh. It thinks they're not identical. That's not good. Maybe I didn't. All right, well, I can't explain that. I'm not sure why this is giving different results. This sort of suggests that all with the double equals is a better option. Yeah, I really don't know what could be. Oh, maybe they're different lengths for some reason. Oh, they're both length m. Yeah, I don't know. maybe next time I'll tell you what went wrong there. Clearly, there's something about the identical function that's not quite working as expected. Okay, so I want to give you a little bit longer exercise this time. So I want to ask you to write a block of R code which produces the following vector. So I'll tell you this vector has length 40. That's helpful, so you don't have to count them. But it starts with 1 and 1, and then it produces the number 2 in the third position. And that's because 2 is the sum of these two numbers that came before it. Then the number 3 is the sum of these two numbers. And then 5 is the sum of these two numbers, 8 is the sum of these two numbers, and so on. So whenever you have an initial segment of the sequence, you can produce the next one by summing the last two values in what you already have. And so you can continue doing that, indefinitely. Here we just do it for the first 40. And I'll just give you a couple minutes to practice that. Yes, this is taking folks some time. That's fine. I'll give you a little more time. Only one person has their answer in. So I'll give you a little more time to iterate on this. And also notice that on the screen share, I'm sort of starting to work through it myself. So if you're feeling stuck, you can kind of look at what's going on there and get a start. All right, so let's talk through it so we can go ahead and move on. We do have several answers here that I'll share. I'll give you just a second as I'm talking to continue to put your answer in. But folks are doing this in various ways. That's good. So this is my way of doing it. So I'm going to create a vector of length 40 to store these values. I'm going to call them fib instead of fibs because that way we can compare the two. I don't want to overwrite this variable. But either way, it's fine. So what I'm going to do here is I'm going to loop through the values. So I'm going to start in position 1 and then 2 and so on. And if I'm before position 3, then I need to assign the value 1 in that position. Otherwise, what I want to do is assign to the next value. I want to say, okay, well, what's in the value right before that? That's fib of n minus 1. And also what's in the value, what value is in the position 2 before that? So that's n minus 2. So like when n is 3, I'm going to assign to fib of 3 whatever fib of 2 is plus fib of 1. So that's going to be 1 plus 1, and I'll assign the value 2 here. But then when n takes on the next value, namely 4, again, I'm going to be in this branch of the if-else statement. And then I'm going to get fib of 4 is going to get the value of fib of 3 plus fib of 2 assigned to it. So that's going to be 1 plus 2, which is 3, and so on. So the point is I can encode the logic for how to progress through the vector in this for statement, and then I can just change this value here however I want. I really should probably call that m and then assign the value 40 to it. And because otherwise, if I wanted to change it, I'd have to change it in 2 places, and that can lead to bugs pretty easily. So this is a little bit better style. But anyway, this is how I'm going to do it. And then let's see what the value fib is at the end of that. And sure enough, this, if we just look at it, this matches up with this one. Let's see whether it's identical. Feels like it has to be. Yeah, there we go. So that's fine. All right, so that's my solution. Go ahead and send that out, and then so I'll just share some of the other solutions people had. I'm going to kind of trust y'all on this because it's hard for me to parse it every one, but you ran it, so you probably know whether it works. So what you can see is that people took different strategies. Like some people just assigned, like here, some people just assigned explicitly to the first 2 positions and then just made a loop that starts from 3. That way you don't have the if-else statement inside the loop. So that's fine as well. Okay, so for loops, again, are important because when you need them, you really need them. But most of the time you want to avoid using them. And so the idea to keep in mind is that vectorization is preferred over an explicit for loop in R because it results in code which is shorter and usually clearer. So an exception would be the Fibonacci sequence. There's not a good way to do that in a vectorized fashion, at least not without using some advanced mathematics to come up with a formula for the nth Fibonacci number. And but that's an exceptional situation. Most of the time we can perform whatever tasks we want with vectorized operations. For example, if you want to square root all the numbers in a vector, you use the sqrt function. That's vectorized. It's a built-in function. It's vectorized by default. Same thing if you want to multiply by some other vector, that is also a vectorized operation. So we've seen that. So if you have a built-in function that's designed to handle vectors, you just use that. It's vectorized. It's all fine. What if you have a function like compute SN, though, that doesn't work element-wise because it's defined in a way that expects a scalar value to come in? So if you call compute SN on a single value, then that's fine. It works exactly as intended. If you call it on a bunch of values, it's not going to automatically apply that function to each one of those values. You would have had to program it explicitly to do that. So for example, if we tried to plug in this whole vector into the function, we get a warning message that's like, hey, you gave me 25 values and I'm only using one of them. So seems like you did something wrong. And indeed, we want to get 25 values here and we only got one. So that kind of stinks. There is a way to deal with this. And that in R, the way to deal with it is to use what's called higher order functions, or special example of a higher order function. So by definition, a higher order function is a function that takes some other function as an argument. So one of the things that higher order functions can do is help us apply the same function to each entry in some more advanced data structure, a vector or a matrix or a data frame or a list. So here we'll talk about, it should say higher order function. Another name for that is functional. But in any case, we'll discuss one that operates on numerical, logical, and character vectors, which is sapply. So the function sapply takes a vector as its first argument and a function as its second argument, and it applies that function to each entry of the vector, as the apply part of the function name suggests. So for example, we can talk about the vector 1 to 10, and we want to square root every entry. So square root is a vectorized function. So we can just call square root on x, but an equivalent thing that we can do is call sapply on x and the square root function, and that's going to produce the same result. So we can see here, if we want, how it produced the same result. And the advantage of sapply is that we can use functions which really can only take scalars, and they're not vectorized. So we saw this compute SN function is not vectorized, and yet we can use the sapply function to get values for it for every number from 1 to 25. So this is the same thing that we saw before, except now we did it without a loop. We managed to avoid having to write a for loop by using the sapply function directly on the iteratable. So this would not have been as tidy if we needed to do a lot of stuff, but since we just need to apply this one function, this is a nice, clean way to do it. Incidentally, if you're used to comprehensions in Python and Julia, which you are if you're in the SI Masters program, because we use comprehensions all the time, especially in Data 1010, but in other classes too. So in Python or Julia, you can just do brackets, let's say x times x for x in 1, 2, 3, 4, 5, and that squares the first 5 numbers for you. So this is a syntax that's very similar to what you might have seen in, a math class, for example. And so it feels very natural once you get used to it. At least for me, I tend to use it a ton. You don't have that in R, and that can feel like a deficiency, but there is this version which is very similar. So you can use sapply and then the values that you want to iterate over. So instead of being at the end here, they're at the beginning, but okay, they're there. And then you can just put the function here directly. You don't have to name it. You can just use the function keyword to define a new function, which does exactly what you want to do to each of these values. So it's very similar. Instead of x times x, we'll just have this stuff here. It's a little more verbose, but it accomplishes the same task in a very similar way. So I just want to mention one thing about this, and then we'll be done. And this is nice timing because this will bring us right up to the tidyverse section, which we can start with next time. So regarding performance with this sapply function, sapply is not as fast as using the corresponding vectorized operation. So square root of a is much faster than sapply of a comma square root, even though you get the same results. And the reason for this is that the sapply loop is an R loop. It's being executed in R as opposed to being executed in the libraries that are defining these vectorized operations. So what's happening is that 1 million times R is presenting a one element R vector, just a single number, to the square root function, getting that result back, and then collecting all of those results and putting them together into a length 1 million vector. And what's happening if you call square root of A is that R hands the entire length 1 million vector to the underlying fast code and says, square root all of these for me. That fast code performs that operation and then hands the whole vector back to the R environment. So it's much faster. It's all being executed by the fast thing under the hood rather than being sort of organized and handled one element at a time by the R language. So just for comparison, this is the same as in Python with NumPy arrays. So all of the same considerations apply. So R vectors and NumPy arrays are very much close cousins. However, in Julia, you don't have this issue. It's quite different. So the code is going to be fast, whether it's code that you write as the user where things are happening at the language level, the Julia language level, or whether it's in some optimized library underneath. So those are all going to be fast instead of just one of them being fast. And it means that you don't have to as aggressively make sure that, you know, as much stuff as possible is vectorized. But in any case, the takeaway here from R's point of view is that you want to use vectorized operations whenever possible, unless you know that you don't need to care about performance, like all of your operations are involving only hundreds or thousands of numbers instead of millions or billions, where it does start to become important whether those operations are executed sort of under the hood where they're fast, or kind of on the surface in the R language where they're going to be much slower. Yeah, this is a great question from Marie. Does it mean that it's better to write functions that take a vector as an input rather than a scalar if you anticipate using it on a vector eventually? Yes, that's exactly right. So anytime you write a function that only handles scalars and you're going to have to apply that to operate on an actual vector, you're going to introduce a performance bottleneck in your code. And again, maybe that doesn't matter. In some cases, you're only handling a modest number of operations, and then it's really completely fine. It's all going to be under a second, no matter what you do. But if you need to be concerned about performance because of scale, the scale of your data operations, then you need to try to vectorize as much stuff as possible. So that's a wrap for today. Apologize for going a few minutes over. We will pick up next time talking about the tidyverse we got right up to that point in the book. So we'll be able to pick up with that next time.